Hey everyone, in this video we're going to go through these derivative problems step by step. And one thing you'll notice right away is that some of the numbers in these problems are pretty large. That was done on purpose. The reason is to show that even when the coefficients look big or intimidating, the derivative rules themselves are still really simple. Once you know the rule, you just apply it carefully, one term at a time. So let's go problem by problem. We're going to find the derivative if f of x equals x squared. So let's start with the most basic one. We have f of x equals x squared. To differentiate this, we use the power rule, which is shown on the top right. So here, the exponent is 2. That means that the derivative is 2x squared, 2x to the power of 2 minus 1, which simplifies to 2x. And that's a very simple start. The next question is the derivative of 6x to the power of 5 plus 18x to the power of 4 plus 21x to the power of 3 plus 2x squared plus 64x plus 521. Now let's move on to a longer polynomial. This one looks more complicated because there are more terms and larger numbers, but the process is still exactly the same. Differentiate one term at a time. So using this power rule, the derivative of 6x to the power of 5 is 30x to the power of 4. The derivative of 18x to the power of 4 is 72x to the power of 3. The derivative of 21x cubed is 33x squared. And then the derivative of 2x squared is 4x. And the derivative of 64x is 64. And the derivative of a constant is always 0. So, putting all that together, the final answer is 30x to the power of 4 plus 72x cubed plus 63x squared plus 4x plus 64. And again, this is why the numbers were chosen to be large. It's to show that even if the function looks huge, the derivative rules don't change. Okay. So, if you guys want, you guys can pause the video and try this question yourself. It's just the same rule. So now, the same idea here is to go term by term. The derivative of 4 over x squared is negative 8 over x cubed. And then the derivative of 8 over x to the power of 5 is negative 40 over x to the power of 6. And the derivative of negative 16x is negative 16. And the derivative of 25 over x to the power of 9 is negative 225 over x to the power of 10. So, the derivative is negative 8x to the power of negative 3 minus 40x to the power of negative 6 minus 16 minus 225x to the power of negative 10. If you want, you could also write it in descending power. Either way is correct. Okay? And next question, we have sine of 3x squared. So now we have a composition. So this is a chain rule problem, as shown on the top right. So here, the outer function is sine u, and the inner function is u equals 3x squared. First, the derivative of sine u is cosine u, so that gives us cosine 3x squared. And then the derivative of the inside is just going to be 6x. So then, we're going to be left with 6x cosine 3x squared. Okay, that's the chain rule. The derivative of the outside, keep the inside the same, and then multiply by the derivative of the inside. So next we have e to the power of 2x. So this is another chain rule problem. We know that the derivative of e to the power of x is e to the power of x, but here the exponent is not just x, it's 2x. So we keep the exponential the same. We get e to the power of 2x, and we multiply it by the derivative of 2x, which is just 2. So we get 2e to the power of 2x. Very quick chain rule example. this one looks intimidating, but it's really just several basic derivative rules combined. Let's do each term separately. So the first term is 6 tan x squared. So we're going to use the chain rule. The derivative of tan u is secant squared u. So we're going to have 6 secant squared x squared times 2x, which you'll just get 12x secant squared x squared. And the second term is negative 58 to the power of x, which we use the formula shown on the right, so the derivative is just negative 58 to the power of x ln 58. The third term is 12x, and the derivative of 12x is just 12. And then we have the derivative of negative ln 5x plus 7, and the derivative of ln u is 1 over u times the u prime. So we have negative 1 over 5x plus 7 times 5, which is just going to give you negative 5 over 5x plus 7. So the fifth term is 350 sine 2x. And as we know from before, the derivative of sine u is cosine u times u prime. So we get 700 cosine 2x, because 350 times 2 is 700. And once we combine everything, this would be our final answer. This is a great example of how even a big looking problem is still manageable, even if you just do one rule at a time. Moving on to the next question. If you guys want, pause to try this question. The formula is shown on the right for the product rule. Okay, so as I said before, the hint is that we use the product rule because we have one function multiplied by another. The product rule is shown on the right. We're going to let f of x equals 5x plus 2 and let g of x equals sine x. And then we find the derivative of each one. So derivative of 5x plus 2 is 5. And the derivative of g of x is sine x, or cosine x. So now we just plug this into the product rule. Our final answer should be 5 sine x plus 5x plus 2 cosine x. And that is the final answer. Let's move on to the next question. This one, we're going to use the quotient rule. The quotient rule is shown on the right. We're going to let the numerator f of x equals 3x squared plus 5x plus 1, and recognize the denominator as e to the power of 3x plus 2x. Now we differentiate each part. The derivative of the numerator is 6x plus 5, and then the derivative of the denominator, we use the chain rule, so then we just get 3e to the power of 3x. And the derivative of 2x is just 2. So we get the derivative of g of x as 3e to the power of 3x plus 2. Now we plug in everything into the quotient rule. We just get 6x plus 5 times e to the power of 3x plus 2x minus 3x squared plus 5x plus 1 times 3e to the power of 3x plus 2 all over e to the power of 3x plus 2x squared. And that's the derivative. This is another good example of a problem that looks long, but really just comes from plugging carefully into one formula. So, overall, the big idea in all these problems is this. Even if the numbers are large, the derivative rules stay the same. That's actually why these examples are helpful. They show that calculus is less about being scared of these big coefficients and more about recognizing which rule to use, whether that's the power rule, the chain rule, the product rule, quotient rule, or like a combination of both. Once you identify the rule, the rest is just step-by-step algebra. Thank you for listening, and see us in the next video.